Hello everyone. Today, we are going to be going over the relationship between time dependence and charging and discharging a capacitor in an RC circuit. Before we get started, let's familiarize ourselves with the question. What is an RC circuit? An RC circuit is a circuit containing resistance and capacitance. Here I have drawn out a situation that contains a voltage supply, a switch, a resistor, and a capacitor in the same circuit. This is an RC circuit. In fact, we can think of this in a much simpler concept. For example, this alternative circuit can have a charged capacitor, a resistor, and a switch. When the switch is closed, the charge will begin to move, and the current will start flowing from the negative side to the positive side. This is what would have happened in the first circuit if we let the capacitor charge and then take out the battery from the circuit. This will cause the capacitor to start discharging. Discharging a capacitor. Let's figure out how discharging works. From Kirchhoff's loop rule, we know that the current has to equal the same from the capacitor to the resistor. Writing this down as an equation, we get current through the capacitor minus current through the resistor equals 0. The current through the capacitor is also the derivative of the charge of the capacitor as time changes, dq over dt. And the current through the resistor is V over R, which we know from Ohm's law. Because the capacitor is discharging, we put a negative sign in front of dq over dt. Charge on the capacitor can also be written as C times V, thus giving us dCV over dt, and the rest is the same as before. We are going to assume that the capacitance is not changing, so we are going to take C out of the derivative. If the capacitance was changing, then we have to go through partial derivatives. But for simplicity's sake, we now have the equation negative C times dV over dt minus V over R equals 0. We want to get dV over dt alone, so we add V over R, then multiply negative 1 over C on both sides, giving us the rate of voltage loss for a capacitor equals negative V over RC, where RC is a time constant and is denoted as tau. Next, we approach this equation with separation by variables by switching V and dt. Then we integrate both sides of the equation with the parameters of V battery and V naught on the left integral and T naught on the right integral. This leads us to the natural log of V battery over V naught equals negative T over RC minus negative T naught over RC. Because T naught is 0, this entire fraction becomes 0. Finally, exponentiate, then multiply V naught on both sides to get voltage as a function of time is equal to V naught times e to the negative t over RC. As I mentioned before, RC is a time constant and can be rewritten as tau. You may be wondering, what is the time constant? The time constant determines how quickly the capacitor charges and discharges. Looking back at this equation, it says that the voltage starts at V naught and is exponentially decreasing and will asymptotically reach 0. If we were to say tau equals T, then the equation becomes V as a function of tau equals V naught times e to the negative 1, which is 1 over e, and it approximately equals to 37%. Therefore, we can say if you want to discharge a capacitor more quickly, you would want to put a small capacitor or smaller resistor in the circuit. A larger capacitor or a larger resistor would increase the capacitor discharging time. And that is a relationship between time dependence and discharging a capacitor. Something noteworthy that we can take away from here is we can also find the charge instead of voltage if we multiply the entire equation by C, as charge is C times V. We are also able to find the current if we divide the entire equation by R, as Ohm's law says V equals I times R. Charging a capacitor. The way that a capacitor charges is not that different from discharging. If we graph the voltage as a function of time, the initial voltage V0 starts at 0 and exponentially grows asymptotically to reach V battery. If T equals tau, the charge of the capacitor will reach 63%. Therefore, we can say a large resistor or a large capacitor equals a longer charging time, and a smaller resistor or a smaller capacitor equals a shorter charging time. The equation for this is as follows. V as a function of time is equal to V battery times 1 minus e to the negative t over tau. We can check if the equation matches the graph by plugging t equals 0 into the equation. This will become e to the negative 0, which is just 1. Then 1 minus 1 equals 0. If t equals infinity, e to the negative infinity is 0. Then 1 minus 0 equals 1. And that is a relationship between time dependence and charging a capacitor. A short recap of what we just learned. RC circuits have time-dependent solutions. Adding a larger or smaller capacitor or resistor will change the amount of voltage, current, or charge going through the circuit.